Hi everybody, now we go to section 10.4 in Calculus 2. In this section, there are three important objectives. The first one is the divergent test, the second one, the integral test, and then the next one is the P-series. So essentially what we do is, we look at the series, we do this section will tell us if the series is convergent or the series is divergent. Pretty much the remaining of the chapter we study about that. How can we tell if the series converge or diverge? Pretty much. That's what we do for the remaining of the chapters. So in this section there will be three tests. Right. So the first test. Now this is the test that will tell if the series is convergent or divergent, but this first test only tell if the series is divergent. So we say if the series converges, then the n terms or the k terms goes to infinity. Equivalently, if the n terms does not go to 0, if the k term does not go to 0, this series diverges. When I took calculus, actually we usually use a of n, and this is what we call the n term test. It's not actually applicable now because we use k instead of n, but what it does is we take the n term. Right. So there's a few things I want to mention here. First, the logic behind this. So what we say here is the implication. We say the series converges implies the limit at k goes to infinity equal the term goes to 0. Now, this is a statement. What we do is, why do these two are equivalent? So that is a matter of logic. I won't explain much, just give you an example here. So if I say I live in Dallas, then I live in Texas. To say if I live in Dallas, then I live in Texas. So this is a statement. I cannot just reverse this because I say if I live in Texas, then I live in Dallas. That statement is false. What is equivalent to this is, I would say if I don't live in Texas, then I don't live in Dallas. This statement is true as well as that. So logically, those two are equivalent. This is a statement that is we call the contrapositive. So if we want something that is equivalent to a statement of something that is equivalent to an if-then statement, we have to reverse it. I mean, write it backward and have to negate the statement. So an equivalent to this is a contrapositive, where we say where the limit of ak, where k does not go to infinity, does not equal to 0, then we're going to negate this and we say the series diverges. So that's why those two are logically equivalent, kind of like this. If we want to switch the if and then statement and we have something that equivalent, we have to negate both of them, and that's essentially what we did here. So that is the logic behind why those two are equivalent. Now, so we know those two are equivalent, but the idea here is this test only tells us if it is divergent, hence the name. Right. So if the k term does not go to infinity, does not go to 0 when k goes to infinity, then the series diverges. If it does equal to 0, it is inconclusive. So what we do is, in the test, pretty much we do this. We will take the limit of the term when the index goes to infinity. If this is equal to 0, we cannot say anything. But if it is not equal to 0, we can say it is divergence. So it only tests for divergence, otherwise it is inconclusive. Right. And finally, so we talk about the logic, what it is actually about. Now actually how the theory works. Now we talk about infinite series, meaning the series that go on indefinitely, goes to infinity. Now if we have a series like you see this one gets smaller and smaller, essentially it goes to 0. Now let's say if the last term does not go to 0, when we add terms into it, it will changing, right? It will keep changing. If we just add something that is not equal to 0 to it, it will change. Now if we add something that is too small or something that goes to 0, adding 0 to it, the sum will not change. So that's why if we want that to be something convergent, meaning that the series have a sum, the sum does not changing all the time, require the last term has to be 0. I mean, we cannot actually get to the last term because the terms when k go to infinity, not necessarily the last term, but the idea is if it just keep changing, the term keep changing, it will not be a convergent because the sum keep changing, and therefore the series does not converge to any number. Now, even though if it go to 0, but it might not go to 0, it might go to 0 too slow. In that case, it still doesn't, it's still divergent. We'll talk about more of that in the integral test, but for now, this is the test, the first of many. Right. So very straightforward. Just take the limit of the sequence. So determine whether the series diverged or state the test is inconclusive. So divergent or inconclusive, we cannot say the series is convergent. Right, keep that in mind. So first, I take the limit as k go to infinity for that. Before we do this, keep this ranking in handy. Yeah, we use this. Now, for this one, k over k plus 1, since k go to infinity plus 1 really doesn't do much, right? So we just take the limit here, and the highest power on the top, the highest power at the bottom. K cancel out is 1, and that equal to 1. Now, if the when k go to infinity, then the sequence not equal to 0, that is divergent. So the series is divergent. Right, next one. Like I said, we just take the limit as k goes to infinity of that. Now, if we have infinity here, we have on the top is a finite number, the bottom is square root of infinity, still infinity. Finite over infinity is 0. Now if that go to 0, that is inconclusive. Just say equal to, why not? Inconclusive. Right, how about this? I check the ranking. In the ranking, say within the power, the bigger function. Now within the exponential function, This one we have is the constant base raised to the index power. So this is in the exponential form, exponential function. The bigger the base, the bigger the function. The 3 to the k powers is a lot bigger than the 1. So 1 is negligible compared to 3 to the k. So if we want to find the limit of that, the 3 to the k, so all I do is just say 1 is significantly less than 3 to the k. So we just ignore it. Since both of them has the power of k, I'll factor it out. 3 over 2 is 1/2. I mean 1.5. Sorry. Now, remember this is a term, a geometric sequence, a term. Now, since the ratio is bigger than 1, this is divergent monotonically, right? But that doesn't matter. What matters is if it is divergent, meaning that the limit is undefined, or actually this one goes to infinity, because if we have the 1.5 raised to infinity, something bigger than 1 raised to infinity is going to be infinity. So in this case, it is not equal to 0. So certainly, this one is divergent. Yeah. So, as long as it is not equal to 0, and infinity is certainly not 0. So the series is divergent. I'm not talking about the sequence. The series is divergent. So let's be clear. So the series is divergent. Right? So, as we see, if we have a bunch of terms, just ignore the terms that are significantly less than the others. Just keep the one with the highest power. If it is ratio, highest power on top, highest power at the bottom, and then we can just rank see what happened there. So here what we have is, by the way, sine of k is between -1 and 1. So basically sine k is less than, so we say sine of k is less than or equal to, this is less than or equal to 1. And 1 doesn't goes to infinity, so we can perfectly write like that. So sine k is going to be significantly less than 5 to the k and significantly less to factorial. So this is the ranking. And because what we don't have on the left here is on the constant. The constant does not go to infinity, therefore is significantly less than ln of n. So constant ln of n, power, exponential, factorial, the tau function, and then the factorial is bigger. So because of that, all of this ranking, that gone, because this one has the highest. This one goes fastest to infinity, so we just take that term if we want to compare. By the way, I should not write that here. I should write that as a limit first. Sine of k, phi of k, 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 the square root of k, why don't we write k to the 1/2, 5k squared, and 3 to the k. Now, this one is significantly less than that and less than that. This one significantly less than the factorial. So all of those three terms, the factorial is the one with the highest power. I mean not the highest power, I should say goes to infinity the fastest. So only that term matters. When this one goes too fast to infinity, the other one doesn't matter. At the bottom, we have the same reasoning. 2, of course, is a constant because doesn't go to infinity. But we have those two terms. The one, both of them are powers, but the square is bigger than the 1/2. So, and then the power itself is less than the exponential. So in this case, if we take out the term that is less significant, we're left with k factorial over 3 to the k. Now even this ranking, the factorial is higher ranking than the exponential. So it goes faster to infinity. Now if we have a ratio, the top go a lot faster to infinity than the bottom, meaning the top is a lot bigger than the bottom. So this ratio will go to infinity because the top is significantly bigger than the bottom. Infinity divided by finite is infinity. Because 3 to the k is significantly less than k factorial. So bigger on the top, this one go to infinity. Infinity is not 0, so the test is inconclusive. I mean, I should not say the series is inconclusive. The test is inconclusive. So it's clear now. Just take the limit as k go to infinity of the term. If it is equal to 0, divergent. If it's not equal to 0, inconclusive. Right. And when we have a bunch of terms, take the one with the highest ranking, meaning the one that goes to infinity the fastest. Right. Now we have another interesting example here. It says the harmonic series 1 over k that is diverges, even though the terms in the sequence, the term in the series go to 0. So 1, 1/2, 1/3, 1/4, and so on. The number does get smaller and smaller, and essentially goes to 0. However, even though the terms go to 0, this is an example of the term did not go to 0 fast enough. That make it divergent. If it go to 0 extremely fast, it will be convergent. But this one, it doesn't go to 0 fast enough. I have just used that kind of idea, but mathematically we don't really say it like that. Right. So even though the term go to 0, which implies it is inconclusive, but later on we can say that the harmonic series, this one, is divergent. Right. We certainly can prove that using the integral test here. So the first test is the divergent test. We only tell us if the series is divergent or if it is inconclusive. We cannot tell that, or we cannot say that if the series is convergent or not. Right. The second test is the integral test. By the name of it, we use integral pretty much. Now, before we do that, need to check 3 things. First, the function has to be continuous, and it has to be positive, and it has to be decreasing. I should not use the decreasing. It should be non-increasing. This is more technical term. More technical, it should be say non-decreasing, non-increasing instead. Well, it should be fine. Right. So 3 things. Before we do any integral test, have to check these 3 things. Next, what we see is, we said if we have those 3 things, then the series and this integral from 1 to infinity. The difference of this is in the sum, this sum, the first term, add the second term, add the third term. So the sum of these Greek terms Whereas when we talk about the integral, let's say the function is like this. We have every point from 1 to infinity, so there's a lot more in the integral than the summation. In the summation we have 1, 2, 3, 4 and so on. In the integral it has every point from 1 to infinity. Right. So suppose we have that. Let's a sub k is equal to f of k. So pretty much a term in the sequence, a term in the series is the same as the integrand in the integral. And so when those three things are true, then it said both of these converge or both of these diverge, meaning that behavior of those two are the same. If one converges, so does the other. If one diverges, so does the other. And important to note that the integral is not equal to the values of the series. So because the sum we add just discrete points, compared to the integral we have the continuous points, all the points, where the series only discrete. Right, we have the first example here. Determine whether the following series converge or diverge. Certainly we use the integral test. So three things we need to check. First one, is it continuous? Second, is that positive? And the last one, is that decreasing? Right. Before we do anything, when we check those things, make sure that we're going to let this be the function. Instead of k, let's use x. So we said let f of x be the function. Instead of using k, we use x. So we're going to let f of x equal to that, and we check those three things. So first of all, it is continuous because the denominator not equal to 0. So it is defined everywhere, therefore it is continuous everywhere. Right. Yeah, usually in this type of function, it is defined and it will be continuous. Is that positive? Definitely, because in this case we would talk about the series. So let x be from 1 to infinity. If x greater than or equal to 1, then that's one certainly positive. So the second one, check. The last one, how do we know if it is decreasing? Right. Luckily we have calculus 1, and when we do this we will take derivative. Derivative of the top times the bottom, subtract the bottom, subtract the top with derivative of the bottom over the bottom square. So simplifying the top, x squared minus 2x squared is minus x squared, and then plus 1. Yeah, x squared minus 2x squared give us negative x squared, and we have negative x squared plus 1, x squared plus 1 squared at the bottom. Now, what we see is because x greater than or equal to 1, even if you put 1 in here, it's still 0. But like I said, we're not worried about that. Worry on the terms. So start from 2, it doesn't matter. But whatever it is, if we put a very big number than 1 in here, the top is going to be negative, the bottom is going to be positive. Always. if we put a very big number in here, bigger than 1, because x greater than or equal to 1. So if we do that, negative over positive is negative. If the derivative is less than 0, of course, in count 1, the series, the function is decreasing. So taking derivative is a way to do that. There's another way where we don't have to do it. And now we just integrate. What will be the limit though? X greater than or equal to 1, so we go from 1 to infinity. So we do that. Now, this in section 8.9 is improper integral, so replace that with the limit. Upper limit, so let's use b. For this one, we can do the substitution for the bottom, because when we let u equal to x squared, the derivative of that is 2x, which cancel with this x here nicely. So that's substitution. Let u just want to be consistent with the way I do things. Right. Let u be x squared plus 1. The bottom. Take derivative. Move the dx. And then divide by 2x. Now changing the limits. X equal to 1 to x equal to b. X equal to 1. U is 1 squared plus 1 is 2. And x equal to b. U is equal to b squared plus 1. Right, just put b in here, and that's what we have. Right, integral. Limit now change from 2 to b plus 1. B squared plus 1. And we have an x on top. X squared plus 1 is a u. The dx is du over 2x. X and x cancel out. The 2 is a constant. Take it outside. So we have the 2 on the outside. And everything cancels out. We have 1 over u du. So pretty much that's what we have. Integral of that is 2. 1 over u. Integral is ln of absolute values of u. That goes from 2 to b squared plus 1. And so that continue equal to limit at b is equal to infinity of 2 ln of b squared plus 1, and then put 2 in. Now since b go to infinity, ln of infinity is infinity. So we have infinity minus some numbers here. Doesn't matter what this number is, but this one equal to infinity. Since the integral equal to infinity, we say that is divergent. But in the integral test, it says that when the function and the sequence satisfy those three things, what happened to the integral will be the same thing as at the series. But it is only in terms of convergent or divergent. We're not talking about the values though. So in this case, divergent. So the series divergent as well. Right. So the limit, the integral is divergent. So the series is divergent too. Yeah. They behave the same in terms of convergent or divergent only. If we have the values of the sum, it will not be the same as the series of the sequence. Right. Next we have this. By the way, there's something wrong with it. Simply, if we're going to put 1 in here, 2 minus 5 is minus 3. We cannot really have negative inside square root. So because of that, let's make it a plus. So make sure that we're dealing with the positive terms here. Right. So first, let the function be that. Let's use x here. And we do 3 boxes. Is this continuous? Is that positive? And is that increasing? So we'll check real quick. So, is that continuous? And I say yes, because for k, for x greater than or equal to 1, if it is greater than or equal to 1, then the bottom is greater than 0. If it's greater than 0, it's not 0. So we divide by something other than 0. It is defined. It is defined, therefore it's continuous. And also the same token, if x greater than or equal to 1, put in here, it's going to be positive. Yes. And is that, because the checkbox are decreasing, right? Sorry. What was that earlier? Yeah, it has to be decreasing. Right. Now, it's easy to see. If we're talking about this function, obviously the bigger the x, the bigger the denominator, smaller the quotient. So yes, this one is just a check. Don't even need to take derivative here because of this. As I just say, as x increases, x getting bigger, the bottom increases. If the bottom increases, the ratio where the top is fixed have to be smaller. So quotient is decreases. Because we have the finite number on the top, we just divide by a bunch of the bottom gets bigger and bigger. Essentially, we have smaller and smaller quotients. So yes, those we check. So now we will check the limit and see what happened for the series. What happened for the integral? That goes from 1 to infinity. So let that be a function for x greater than or equal to 1. Yeah, so we just integrate this. Right, so it's not that bad. We just do a substitution, u equal to 2x plus 5, and then so on. Right, let's say, correct. First there's infinity, so we'll take care of that. With the limit now we just do the substitution. Let u be 2x plus 5. We take the derivative. So du is 2 dx, and du over 2 is dx. Now the limits changing from originally x equal to 1 to x equal to b. So x equal to 1, u is 2 times 1 plus 5, so it's 7. X equal to b, u is equal to 2b plus 5. So now the integral becomes, the limit will change from 1 equivalent to 7, and then 2b plus 5. And then we have 1 over square root of u. Dx is du over 2. Take that to 1/2. We write this as negative 1/2. And integral of that, increase the power divided by the same thing. Since at the bottom 2 and 1/2 can cancel out, we do have the limits though. 7 to 2b plus 5. So we substitute that in here. We have 2b plus 5 to the 1/2 minus 7 to the 1/2. Now, since we go to infinity to the 1/2 minus 7 to the 1/2, because it's infinity. If it is infinity, this is divergent. Now, if the integral is divergent, the series is divergent. We say the series diverges. Right. So just check integral. Before using the integral test, check in those 3 things and make sure that in the homework you might have to consider there's a function the same as the the sequence. So yeah, so that is the integral test. Actually, we will do one more integral test. Let's see something. Actually, we'll talk about that in a minute. Right, P series. Now this is a lot more applicable. This is a special case of the integral test, but we use this a lot more than the integral test because it is easier to see. So it says when we have the series in this form, it's called the P series, 1 over k to the p, because p is the constant. K is the index, so we have like 1 over x squared, 1 over x cubed, something like that. Now, it's very easy, very clear. It is converges if p is greater than 1 and diverges if it's less than or equal to 1. So straightforward. If we can find p, and the rest pretty simple. Right. So to rewrite this, now the next question is, does it matter if we have k equal to 1 goes to infinity or not? The answer would be no, it doesn't matter. I'll explain in a minute. Anyway, fourth root of k cubed we can rewrite as power on top, root at the bottom. Now this is a P series where P is equal to 3/4, and that is less than equal or equal to 1. Because of that, this one, the series diverges. So that's what we do, really. Just write that in the right form and determine what is P. Less than 1, equal to 1, divergent. Greater than 1, convergent. Right, next. Before we do anything, note that in the P series, this has to be just the index. It cannot be something else. So I'm going to change the index first. To change the index, let's say we need this just to be the index. So we can say let n equal to k minus 1. When we substitute in here, just 1 over n squared, right? When n equal to k minus 1, we can say k equal to n plus 1, and we can substitute in this series. Now instead of k equal to k, we use n plus 1. K is n minus 1, n plus 1, sorry, and then we have minus 1 square. Now, for here we subtract 1 on both sides, so I have n equal to 3. We have 1 over 1 cancel out n squared. So this is also a P series where the index raised to the power. And the P series where P equal to 2 and 2 is bigger than 1. Therefore this one is convergent. So that's simple enough, right? Now, just want to write a little note here. This series, even though it starts at 3, but it should not be a problem, because the first thing we learned from the previous section is that, it says here, in general, where their series converges does not depend on the finite number of terms added to or removed from the series. So what we did is we removed a few terms in front of this. We start from n equal to 3 instead of n equal to 1. But it doesn't matter. What it matters is when it goes to infinity and in the right form, the P series is bigger than 1, converges, less than 1, diverges. By the way, let's use the integral test real quick. Let's say if we want to do the integral test for 1 over x squared, or we say the series is 1 over k squared. So of course, if we have the function 1 over x squared, 1 over x squared, that is positive continuous for x greater than equal to 1, and it is also decreasing because the bottom getting bigger and bigger. For bigger values of x, the quotient is smaller. Because of that, this is decreasing. So all three things check. Now we're just going to do the integral from 1 to infinity of 1 over k squared, 1 over x squared dx. So this is simple enough. Improper integral replace b with the limit. And we integrate. Integral of x squared is x to negative 1 over negative 1, going from 1 to b. Now substitute in b. Put the minus, don't forget that. And substitute into 1. Right. Substitute for b, substitute for 1. That's what we have. And b go to infinity. But before we do that, I will move the b to the bottom like that and turn that into like that. Now since b go to infinity, this one goes to 0 and integral go to 1. Now it go to 1, meaning that it is convergent. So we say that the series is convergent. The series does not equal to 1. The values of the limit, the values of the integral has nothing to do with the values of the series. The only thing that they are the same is they are both convergent or both divergent. The values may or may not be the same, but usually not. Right? So this is an example. The integral test will show that this is convergent. However, if we use the P series, we get the answer immediately. Right. So in this section, there are 3 important tests: divergent test, integral test, and then even though a subset of integral test, that's the P series. So P series, integral, divergent test, and this kind of a little advantage, not a little advance for the integral test. So let f be continuous, positive and decreasing for x greater than equal to 1. So all those 3 ingredients for the integral test. Now h of k equal f of k is all of that are required for integral test. We said the series, let the series be convergent, and that is the sum of the first n term. So s is the sum of the first n term. I think I make a mistake here somewhere. So that is the infinite sum. This is s sub n, and this should be n. So going from k equal to 1 to n, that will be the sum of the first n terms of the series. In that case, the sum of the whole infinite series minus the sum, the partial sum, satisfy this condition. Furthermore, if we solve for that, the series will be bounded between the partial sum plus that and the partial sum plus that. Right, so we say the actual integral plus s of n, so those two is that. Right, so once again, the remainder, the difference between the infinite series and the partial sum satisfy this condition, and we have the bound like this. Let's look at one example. Consider the series here. How many terms must be summed in an approximation that is within 10 to the negative 3 of exact values? Right, so all we do here is just do the integral test. So first of all, we go to say r sub n, the remainder is going to be less than integral from n to infinity. Don't know what n is yet, but so in that case we would write the integral from n to infinity of f of x, which is let f of x be 1 over x squared, and we did show that earlier. Continuous, positive, and decreasing, all three are checked. It is decreasing because the denominator getting bigger, the whole quotient getting smaller. Because it's getting smaller, it is decreasing. So that makes sense. So we're going to do that. And again, for infinity, so replace that with the limit of b goes to infinity. This I can write x to the negative 2. So we do integral. By the way, I'm just going to ignore the second part of the problem. That's very easy. We're just going to do that. Right. So integral of that is x to negative 1 over negative 1, going from n to b. And that's moved to the bottom. We have negative 1 over x, b, and n. Right. Like I said, I will omit the second part of the problem. Now put b and then put in n. And that cancel out now when b go to infinity, put in here that go to 0. Finite divided by infinity is 0. So we have just 1 over n. Now this have to be within 10 to negative 3. So we're just going to say like that. So we have 1 over n less than 10 to negative 3 is 1 over 10 cubed. Now if it's like this, when we flipped the positive fraction, we have to reverse inequality. For example, 1/2 greater than 1/3. 1/2 is greater than 1/3, but when we flipped, we'll reverse the inequality. So when we flipped, so like that, which means we have to have more than 1,000 terms for this to work. So this theorem says that how many terms we have to use in order to achieve some certain remainder. So the actual values between the whole series and the particular the partial sum. But I said that's nice and all, but I'm not going to don't need to focus on this. Focus on 3 things: divergent test, integral test, and then the p-series. P-series kind of inside the integral test, but if we know that, we don't have to do the integral test. All right. So like I said, the remaining of the chapter we're dealing with a lot of tests. So the test is just telling if the series is convergent or divergent. Usually it's just convergent or divergent. On the rare occasion we can tell the sum though. Very rare occasion, like the telescoping series, we can find the sum if it's actually convergent. But most important, there will be like 9 or 10 tests, and then we just need to show that if the series is convergent or the series divergent. That's the important for the whole chapter, not just in this section. In this section we have 3, but later we have a lot more later. So with that, I've stopped the video here, and thank you for watching.